All we've looked at so far is objects that move perfectly vertically or perfectly horizontally, and now we're looking at things that make an arc, right? That move both in the vertical and horizontal direction. Those are called projectiles. Have you heard that word before? Right? Projectile motion is motion that moves like in an arc pattern. So we move both horizontally and vertically at the same time. But to get there, we have to start a little bit more basic than that. So we're going to talk specifically back about vectors. Do you remember when we introduced vectors the first time? How do we represent vectors? With an arrow, good. Vectors are any quantity that have to have a magnitude and a direction, right? That should be a review part for us. Anything that has a magnitude and direction. So far, the three that we've talked about are displacement, velocity, and acceleration. Those are the three vectors that we've covered so far, okay? Scalars are the what is that missing? What part is it missing? No direction, right? So scalars are any measurement that does not need a direction. So any quantity that just has the size, and then we don't ever indicate direction with a negative, right? So scalars would never be negative, okay? The things we've talked about here with that are scalars are distance, speed instead of velocity, right? Once we get past this chapter, I think it's okay. Actually, once we get past the last chapter, I think it's okay that we use speed and velocity interchangeably. We understand, or we should understand that, that they do have fundamentally different definitions, right? Speed really is distance over time, velocity is displacement over time. But you'll kind of notice that after this chapter, we start to use them interchangeably, which is not technically correct, but it happens. Okay, so I just want you to kind of be aware of that. We do understand, I hope, that there is a difference, but they start to become a little bit intermingled. So, all right, when we talked about vectors the first time, we introduced what's called the tail to tip method, right? And that is where we add our vectors one right after the other, okay? And when we had the tail to tip method, we start to look at how we put them together, right? And we kind of introduced the fact that it doesn't really make a difference what order in which we add our vectors, right? Because if I were to go, if I were to start here, walk east, then walk north, and end up at this spot, I could walk north the same distance and east the same distance and still end up in that spot, right? It does not make a difference the order in which my vectors go, okay? So that's one thing about vector addition. They can be done in any order. We can add any number of vectors, and then the resultant vector. Do you remember what the resultant vector is? What's kind of the term for the resultant vector, or the definition of the resultant vector? Resultant vector is like the sum of all of the vectors, right? The sum total of all of our vectors. So yeah, we looked at introductory types of vector addition where, same thing, if I was going to walk east, then north, then my resultant vector would go from the origin to the tip of the last vector, right? It tells me exactly how far I am from where I started, right? So it's a sum total of my vectors. So in this example here, which one of them is my resultant vector? The red, blue, or black? Red, right? We've got a 12 Newton vector that's going north, 9 Newton vector that's going north, and then our red one goes from the origin to the tip of the last vector. So the red one in that case would be our resultant vector. Okay? Sometimes resultant vectors are extremely simplistic, like that example, and sometimes they have to go a long way, right? They go a long way at an angle. So, all right, we're going to practice first adding our vectors graphically. So there's two ways that we can do vector addition. The first of which is graphically, and we need a ruler for that. The second way I'm going to show you is the way we'll use more often, and that's just like mathematically solving them. So I'm going to show you both, but I want you to grab a ruler real quickly so that we can add these graphically. So, all right, so we're going to practice adding graphically, and since I printed the slides, I'm not sure if you have room on the slide to draw it, or if you want to get a scratch piece of paper, or whatever you want to do is up to you. But when we add things graphically, the scale in which we draw our vectors becomes really important. Okay, do you know what a scale is? Right? It's like when you look on a map and the map says 1 inch equals 20 miles, right? That's a scale. And so when we draw our vectors graphically, we have to determine a scale. And really it's up to you what your scale might be. But I want you to add these vectors graphically. So we have 5 vectors here. D just stands for like displacement 1, right? It's a displacement vector. This first vector goes 10 meters south. The second vector goes 30 meters west, right? So when you add them graphically, you're going to actually draw these vectors to scale and then draw your resultant vector and measure that resultant vector. Okay, so let me kind of give you an idea here. I'm not going to draw it to scale, but you guys are. You're going to determine what your scale is. But I'd go 10 south, 30 west, 90 south, which I don't have room for, 50 east, there, and 40 north, right? And so my resultant vector goes from the origin to the tip of the last vector. So I'm drawing all of those blue vectors to scale and then measuring that purple one, and we're going to see what our resultant vector actually should be. Does that kind of make sense? So you can choose your scale to say 1 meter equals 1 centimeter on your ruler. You could say 10 meters equals 1 centimeter. That'd give you a pretty small one. Whatever you want to make your scale is fine, but I'm going to give you a few minutes to get that drawn, and we're going to get that purple measured the purple vector measured as exact as you can, and we'll see. Well, then we're going to solve it mathematically and see who's closest. So let's go ahead and now, once we've got this measured and done, we're going to try to check it, because this method does not allow us to solve for the angle very efficiently. So let's grab your calculator out. We're going to try to find what is the length of this resultant vector. How could I do that? Can't I make it a right triangle? Right? So how do I know the sides of those triangles? Of that triangle? Right? Isn't this 10, 30, 90, 40, and 50, or other way around? Is this one 50? Yeah. Okay. So that means if I went 10 south, 90 south, 40 north, what does the side of that triangle have to be? I think it's got to be 60, right? Because 10 plus 90 is 100. 40 back up from that would leave me with 60 meters there, right? And mine is not to scale, mind you, right? So it looks a little off maybe, but that's going to be about 60 on that side. And then what about this side right here? What does that have to be? I went 30, then I came back 50, so this side has to be 20 meters, okay? So now this will allow me to solve this hypotenuse and check, because it should be the same as one of our measurements over here. So let's mathematically go ahead and solve for the hypotenuse of that triangle. How do we do that? Pythagorean theorem. We're going to get really good at Pythagorean theorem and trig functions. Okay, so Pythagorean theorem is a squared plus b squared equals c squared. So I'm going to go square root of 60 squared plus 20 squared. And I get 63.24 meters. Right? So those of you that said 63, that means you're pretty darn close. Okay, 63.24 meters. But this is still only the magnitude of that vector. It's not magnitude and direction yet. And so remember, we did this originally, but let's think about it again. If I want to include the direction, I have to include either this angle or this angle to tell me how am I going to get to my final point. Okay, I always just encourage you to find the angle of the triangle you are working with, right? There's no use to find the, complementary or supplementary, whichever one it is, right? There's no use finding that one. Just find the one with the triangle you're working with. Okay, so if I want to find this angle right here, I technically do have all 3 sides of my triangle because I already found the hypotenuse. But when I do this, I always use the sides that I was given, because if I miscalculated the hypotenuse, then I'll miscalculate my angle too. You know what I'm saying? So to find this angle right here, I always use tangent. Okay, because tangent is opposite over adjacent. Agreed? Do you remember that? Do you remember the sine functions? Sine, cosine, and tangent? So if I want to find the angle in my calculator, I have to use second tangent. Second tangent of opposite over adjacent. Okay, I do want to make sure that your calculator is in degrees, not in radians. So especially for calculus, you might have to switch back and forth. That might be the only class that you'll use radians in. Maybe pre-calc, I don't know. Okay, but do you know how to check to see if your calculator's in degrees or radians?
No.
Yeah, it's in mode, okay? And you want degrees to be darkened. So this class always needs to be degrees, okay? So I'll go second tangent of opposite over adjacent, and that gives me an angle of 71.6 degrees, okay? And so that's this angle right here. 71.6 degrees. So this is how we label our answers. 63.24 meters at 71 degrees, and then we have to decide the cardinal direction that goes with it. Right? Here's the origin. And so here's my angle right here. Is that angle north of west, south of east, east of whatever, whatever? Can you envision that? This is east, north, west, south. It is south of east. 71 degrees south of east. Okay, let me make this a little bit cleaner up here. Here's the origin. Here's my hypotenuse. That's the angle I'm looking at. Okay, so to find that angle, the first thing I look at is what axes is it touching? Well, it's touching the east axis. And then I decide, does my triangle swing north of east or south of east? Right? It swings south of east. So that's the way I kind of tell that. It's got to be touching one of the four cardinal directions. It's touching the east axis, and then I decide, well, it swings south of east. So let's say that my angle happened to be going, let's say my angle was this one right here. Let's say that I was looking at a triangle like that. So what direction would that angle be? West of south, right? West of south. So it's touching the south axis, and it's not swinging east of south, it's swinging west of south. Okay? You can also think about it as those directions going opposite of the way you went. So I went south first, then west would mean west of south too, if you want to think about it that way. I don't love that one as much, but okay? All right. So that's how we do it mathematically. That's going to be how we solve vectors 98% of the time, right? Is with the math part of it, using Pythagorean Theorem, using the tangent function, things like that. So let's look at another one here. This same type of thing, but a simpler vector problem. Okay, so a person walks 10 kilometers east, then 5 kilometers north. What is the resultant? So the resultant has to include magnitude and direction. So that means we have to include the hypotenuse and the angle. Okay, we're going to always try to get ourselves to a right triangle, and we're going to be able to solve hypotenuse and angle. So 10 kilometers east, let's say each of these boxes is 2 kilometers. 2, 4, 6, 8, 10, and then 5 kilometers north. Should I do this to go 5 kilometers north, like that?
No.
10, and then 5, like that?
No.
Isn't my hypotenuse going to be the same? Yes, but what's my problem? Yeah, well, okay, yes, but it doesn't take me anywhere from my origin. Right? The resultant vector always has to go from the origin to the last vector. So if I put on my vectors like this, like, yes, technically my hypotenuse would be the same, but then you're like, well, what angle do I find? Right? I have no idea which angle I'm supposed to be looking at because neither of my angles touch the origin. Right? So that's a problem. Always tail to tip. So after one goes the next one. And then my resultant vector goes from the origin to the tip of the last vector. And this would be what I'm solving for. I like to kind of put in a question mark to just remind myself, like, I'm solving for the hypotenuse, and I'm also solving for the angle. Always the one that touches the origin. Okay, always the one that touches the origin. So this side would be 10. This side would be 5. So we solve with Pythagorean Theorem and again with tangent here.
always looking for the angle that's next to the origin.
Has to touch the origin. Yep. Because the angle is telling us, if I start from the origin, where would I need to leave? Like, in what direction would I need to leave to get to that point? That's the whole point of the resultant vector. It's telling us I need to leave at this certain angle. So when I did Pythagorean theorem, I got 11.2, it would be kilometers. At what's my angle here?
26.6.
Good. 26.5 or 26.6, right? 26.6 degrees. What of what? North of east. Very good. Right? North of east. It's touching the east axis and it swings north. Okay? North of east. So that is what constitutes a complete answer. We got magnitude and the angle. Okay, I want to point this out. If I had added my vectors in a different order, if I had gone north and then east, I still get to the same position, right? Hypotenuse is still the same, but what's different? The angle I would find would be 90 minus 26.6, right? Or it would be opposite of 10 over 5. So my angle would come out to be 63.4 degrees east of north. Both of those answers are correct. Okay, both of them are correct because they're, I don't know what it is, complementary or supplementary. I don't know which one adds up to 90. Okay, it's one of the two, complementary, I think. But those angles lead us to the same final destination. So this angle is correct and this angle is correct. It would not be correct to say 26.6 degrees east of north or 63 degrees north of east, right? That would lead us to here. So you've got to make sure that you've got them labeled correctly, but I would accept either answer. So it doesn't matter which order in which you add your vectors, but you could use either of those angles and still have it correct. Does that make sense? Okay. All right. We've already kind of talked about this, so I'm going to skip over this. Now I'm going to talk about when we're given a vector at an angle. Okay, what happens if it says they walk 35 meters per second at 40 degrees north of east, right? Well, we draw that angle. So if it says we go 35 meters per second at 40 degrees, we've now got this vector drawn at an angle, but we can't work with things in physics that go at an angle, okay? Because let's think about here. Our overall goal is to get back to working with projectile motion, which moves at an arc, and we always have to solve components in physics as vertical, separate from horizontal, right? We can't work with things at angles. We can give answers that have angles, but we can't plug things that have angles into an equation. Does that make sense? The vertical component and the horizontal component of motion has to be analyzed separately, like completely separate. So when we're given a vector at an angle, the first thing we have to do is break it down into what we call its horizontal components and its vertical components. It's basically like we're given an angle and then we draw the triangle to complete that and we find what the sides of that triangle are, right? We break that into its components. So you'll see me label them, Vy if it's a velocity vector, Vx if it's a velocity vector. So we're going to start to have a bunch of subscripts added. Vy would mean velocity in the y direction. Vx would mean velocity in the x direction, right? We're going to have to start adding these labels to our variables, but all of those labels mean something. Okay, does that kind of make sense? So they're going to have these vertical and horizontal components, okay? So I put a trig review in here. Do we feel okay about trig functions? Opposite, over, okay. I'm not going to talk about this, but it's in there if you need to go back and reference it, okay? So if I was looking at some vector v, right? Some vector, I've got an angle here, and this would be its x component and its y component. Do you know why they're labeled x and y? Right? This one, because it's horizontal, x, because it's vertical, y. Okay, so we got to feel really comfortable about x being horizontal, y being vertical. All right? So let's look at this one. It says the helicopter's flying 34 meters per second at 25 degrees south of west. What are the components of the velocity vector? Okay, it's got the triangle already drawn for you. The 25 degrees fits, right here. It just couldn't squeeze it in there any closer, but it fits right there. So what would I label the green side of that triangle? Vx, and this red side would be called Vy. Okay, so let's go ahead and solve that now. We can't use Pythagorean theorem because we only have the hypotenuse, but we also have an angle, right? So if I was going to look at this x side first, what side is that in comparison to the angle? It's adjacent. Okay, so in that case, I have adjacent and hypotenuse. So what would I use? I would use cosine, right? Okay, and so if I was going to set up that equation, it would look like this. Cosine of 25 degrees equals the adjacent side, or Vx, over my hypotenuse. Okay, do we agree? That's how it would get plugged in? Okay, so now here's how I typically write it. If I want to solve for Vx, what do I have to do to the 34? I have to multiply it over. So realistically, Vx is the same as saying 34 times cosine of 25. Is that a I don't, are you used to seeing it written that way or not really? Yeah? Okay, good. Okay, that's how we're going to do that. So that would be equal to Vx, right? Hypotenuse times cosine of my angle. Let's go ahead and plug that in and see what that looks like. So 34 cosine 25 gives me 30.81. Okay, now here's what we have to really pay attention to from now on. Does this vector, my x component of my vector, is it going east or west? It's going
west.
West. Okay, and so what does that mean my vector has to have with it?
Direction.
Okay, it has to have a direction, but more specifically, we can't just do cardinal directions now. It's got to be a negative, right? We're going to add that negative for any vector component that's south or west. Okay, because when we start mathematically adding our vector, the negative is the only way for us to indicate direction, right? We can't mathematically indicate west with just a W. We have to include it in a negative form. So the x component here would be negative 30.81. And so as I'm looking now at the y component, I would use what? Sine or cosine? I would use sine, right? Opposite means I'm going to use sine. So sine of 25 equals Vy over 34. So again, I'm going to start to just write it this way. 34 times sine of 25. So does that feel comfortable with everyone if I write it just in that format? Okay, so I'm going to take 34 times sine 25, and I'm going to get 14.4. And that one has to be negative as well, right? Because it's going south. Okay, it's going south. Okay, and then that's it, right? That's all it asked for was the components of the vector. Why don't you go ahead and try this one on your own? A vector represents a displacement of 500 meters at 30 degrees north of east. What are the magnitudes of the vertical and horizontal components? Okay, so we got to now look at how to draw that angle. Do we feel okay about that, or do you want to see how I do that? Okay, if I'm going to draw the angle 30 degrees north of east, I always draw the origin, and I draw my angle just arbitrarily northeast. Okay, and then I decide, well, where does my 30 degrees need to go? Does it need to go on this side of my triangle or this side? Right, so if it's supposed to be north of east, which way does it need to go? Like top or bottom of that? It needs to go bottom. 30 degrees goes here. And then vector components are usually drawn as dotted lines. So I kind of draw my components in like that. So when I have to draw a vector at an angle, that's kind of how I do it. I draw it kind of arbitrarily in that direction, and then I assign where the angle goes from there. Okay, so I had 433 for my x and 250 for my y. Okay, so I didn't really draw mine to scale because my x looks not quite that long, but that's about what we're looking for there. Okay, do we feel okay with breaking them into components? Okay, so now we're going to do one final problem here that kind of puts it all together. Now we've got multiple vectors we're going to do this process with. Okay, so this next one says, a mail carrier leaves the post office and drives 22 kilometers in a northerly direction. That just means due north. Okay. She then drives a direction 60 degrees south of east for 47 kilometers. What is her displacement from the post office? Okay, so if you look at your next slide, it has the drawing of what that looks like, but I don't think that serves a good purpose for us, and I'll tell you why. Okay, drawing it out only allows me to see that my resultant vector would look like this, right? But that's not very helpful because there's not a right triangle formed out of this, right? This does not make a right triangle. I could make one, but I'm going to do that when I add them when I add them mathematically anyway. So I'm really not even going to bother drawing out the vectors together like that. I'm going to just kind of cut that part of the problem out, and I'm going to just look at the vectors as individual vectors and solve their components individually. Okay, so you can draw out the full picture, but I think sometimes it almost makes it more confusing than to just do them individually. Okay, so here's the method that I would use here. The first step is to break each of our vectors into x and y. So we've got two vectors here, 22 kilometers north, and then 47 kilometers, 60 degrees south of east. So we've got two vectors we've got to pay attention to here. And I'm going to treat them each separately. So I want to look at vector 1, which we'll just call this one right here, 22 kilometers north. So I'm just going to call it V1. And I'm going to draw what it individually looks like, 22 kilometers north. Okay? No angle that goes with that. So I'm gonna still consider the x and the y components of this vector. So that means v1x would equal what? V1x. It would be 0, right? Because there's no horizontal part of this vector at all. It's only going north. So that means v1y would be equal to 22 and positive 22 because it's moving north. Okay, so that first vector, when they're moving in a true cardinal direction, one of those components is always going to be 0. Okay, vector 2 now says it's 60 degrees south of east, 47 kilometers. So I'm going to draw it southeast. And I've got to decide where's my 60 degrees have to go. South of east. So is it going to go here or here? I think it's going to go right here. South of east means it needs to touch the east axis, then go south. Right? So here's where my triangle is going to get formed. And that's going to be my 60-degree angle right there. Right? Because we're touching the east axis, going south. 47 is my hypotenuse there. Okay, so this one will have both an x and a y component. So if this vector is called V2, because it's my second vector, I would call this side V2x and V2y. Then I'll just come down and solve. Now, I want you to kind of pay attention. Up until this point, our x's have all been cosine. That's coincidental, because when I have an angle that is here instead, x would be opposite, not adjacent. So I don't want you to just memorize that x is always cosine, y is sine. That's really not the case, but it has been that way so far, coincidentally. Okay? So really pay attention to, is x going to be adjacent or opposite? In this case, it's adjacent. So we would go 47 cosine 60. And for y, we would do 47 sine 60. Okay? Okay, do either of these components need to be negative? Yeah, which one? The y component does need to be negative. So x, I think, comes out to 23.5. And y, I think, comes out to negative 40.7. That's like step 1 of vector addition problems, is break each vector into x and y. Step 2 is to add our x's together and add our y's together. Add the x's together and add the y's. So I like to kind of put myself into a pattern down here. Like I always solve for x first. That just keeps me a little more organized and kind of helps me keep things in line. But when I add my x's, I'm going to call this resultant x and resultant y, right? Because I'm finding essentially the components of my resultant vector. If I would go look at my resultant, like on the next slide, if you would draw that resultant vector, the sides of this triangle are essentially what we're solving for right here. Okay, so add my x's. 0 plus 23.5 gives me 23.5, and 22 minus 40.7 gives me negative 18.7. Okay, so vector addition is in its most basic form 3 steps. Break each vector into x and y, add the x's and add the y's, and step 3 is build a new resultant triangle based on this resultant information. Okay, so these are the sides of our resultant triangle. So I'm going to come up here and I'm going to start my origin. It doesn't matter if I go east first or south first, right? The x component is positive, which means it's going to go east. The y component is negative, so it would go south. I'm going to go ahead and go east first, 23.5, and then I'm going to go south, 18.7. We don't have to include the negative on the triangle because the negative just told us what direction to draw it. Okay, so we don't include the negative when we do the math right here. But now this is our resultant vector. This is telling us how far she is from where she started. Okay, how far she is from where she started. Okay, I want to just look at one thing real quick. Okay, and I'm going to go to that next slide for a second. Okay, do you see how if I were to draw the components like that, my resultant vector goes southeast like that? Okay, that's pretty darn close to what it looked like when we drew it here. Okay, right, we did all of our math and we drew it. That's pretty darn close, right? We're supposed to be going southeast. That's what it's looking like. So that means we did it right? Our resultant vector is at least going in the direction we expected, okay? All right, let me get back to that previous one and we'll finish this up. Okay, so last step, build a new triangle. So we've got the sides of that triangle. Now all we've got to do is find that resultant hypotenuse and the angle that goes with it. So we're trying to find that and the angle. Okay, so Pythagorean Theorem. I'm going to write it up here at the top. 30.0 kilometers at, I'm going to find the angle here. I'm going to use second tangent, 18.7 over 23.5, and I get 38.5 degrees south of east. Okay, so it's a lot of work, right? It's systematic, but it's a lot of work, okay? The algebra that goes into it, not difficult, but it just could be a lot if there's especially more than 2 vectors. So I want you to kind of remember that process if we have more than 2 vectors. Break it into x and y, add your x's and y's, build your new triangle, right? That's always kind of your steps, okay?